So this lecture is going to be about simple harmonic motion, which is not very simple. So let's get started. So before we start talking about the equations for simple harmonic motion, we need to talk about some definitions. So the first one is an oscillation, and that is just a movement back and forth at regular intervals. So this could be a pendulum swinging back and forth. It could also be a mass on a spring moving back and forth like this. But as long as that happens at regular intervals, we call this an oscillation. Now, period is something that you have heard before, and this is denoted as a capital T, and that's the time for one complete cycle. So we talked about period when we talked about uniform circular motion back, in one of our previous chapters that we learned about. The unit for period is seconds. And then we have this term called frequency, which is denoted by a lowercase f, and this is the number of times per second that the object completes a full oscillation or a full cycle. So an example of this would be like 200 cycles in 2 seconds. We would divide that 200 cycles by 2 seconds and get a frequency of 100 hertz. So something that is very, very frequent is going to have a higher frequency than something that is not as frequent. We'll have a lower frequency. Now this unit hertz, this means 1 per second or 1 cycle per second. That cycle term kind of drops out. That's what I call kind of a ghost unit. So that 1 hertz equals 1 per second. So anytime you see 50 hertz, 100 hertz, 200 hertz, basically all it's saying is that there's 200 hertz or 200 cycles happening per 1 second, or maybe 50 hertz, 50 cycles happening per 1 second. Now frequency and period are reciprocals of one another. They're inversely related. So frequency is equal to 1 over period, and period is equal to 1 over frequency. Now, last but not least, this is also called periodic motion or just harmonic motion. And this is just any motion that repeats at regular intervals. So like I said before, this could be a mass on a spring, and here I'm showing a vertical mass on a spring, but we also have the example of a horizontal mass on a spring that we use a lot, or it can be something like a pendulum that just swings back and forth. So since these things both have a period, or the amount of time that it takes to complete one cycle, this is called periodic motion. Now, some more definitions here is number one, this point where we have like a spring or a pendulum and it's relaxed, we call that the equilibrium point. So this is our relaxed position, and you'll hear me talk about the equilibrium position a lot in simple harmonic motion. We also have the 2 points where that mass is farthest away from the equilibrium position, and this is called the amplitude. So this is the maximum displacement from equilibrium. This is denoted by a capital A, or you'll sometimes see X sub m as in maximum X position from the equilibrium position, because equilibrium we call X equals 0. So that's what the M means. It means maximum. Maximum force here is going to be at the 2 amplitude positions. And if you recall from chapter 8, we talked about spring force, and spring force, or Hooke's law, that's equal to force is equal to negative kx. And the reason that that force was negative is because it's a restoring force. I'll talk about that a little bit later. But we can see that the force is going to be proportional to the position away from equilibrium. So here, the higher that position gets, so the higher x gets in that equation, the higher the force. So that's why at our amplitude position, or our maximum position away from equilibrium, we have a maximum force. So because we have maximum force at those 2 amplitude positions, we also have maximum acceleration, which we'll talk about later. And then last but not least, we have a minimum force when we are at the equilibrium position, because X equals 0 here. So since X equals 0, spring force is equal to 0. This can also be applied to a pendulum, which we'll talk about more later. But our restoring force in a pendulum is going to be one of the components of the gravitational force, because gravity is what's pulling it back to that equilibrium position. So our X component of the gravitational force is the one that's going to be pulling it back horizontally to that equilibrium position. All right, so simple harmonic motion. The reason we're here today. This is a sinusoidal function of time t. Now, this can be written as either sine or cosine of time t. We usually do write it as cosine though, and I will talk about that on the next the next sentence. But also, I do want you to watch that portion of the simple harmonic motion video from Crash Course that I'm talking about to kind of show you where this equation is really derived from. I'm not going to derive it for you here, but they have a really good graphic in Crash Course to really show you where it comes from and hopefully better understand this equation I'm about to show you because it looks crazy. All right. So we usually write this equation with cosine because we have to disturb the object from equilibrium to get it to oscillate. And I'm going to show you what I mean by that on the next slide or the next couple slides. I'm going to compare a sine and a cosine graph. So this is our equation for the displacement as a function of time in simple harmonic motion. So we have our displacement as it varies with time. And that's going to be equal to our amplitude times the cosine of the phase. And this phase right here, which is this whole thing in the parentheses, this phase is our angular frequency, which we've learned before, omega. We talked about this in our rotational motion, times the time plus this phase constant. Now, the phase constant is there, and we also could call this the phase angle because we might shift this graph depending on when we start our time t. Sometimes it just drops out, and I'll talk about that a little bit more in a second. But this is like the entire equation. Sometimes we don't have the phase constant there, sometimes we do, but this would be your general equation for displacement as a function of time in simple harmonic motion. So this is something that's moving in simple harmonic motion, and you can see that it looks like a sine or cosine graph, which is why we are using cosine in our equation. It also looks like a wave. So we don't talk much about wave motion in AP Physics C mechanics, but this motion is like a wave, this simple harmonic motion. And again, here is the cosine graph in blue and sine graph in yellow. And what I mean by we have to disturb the object from equilibrium, this right here would be our equilibrium position. So in order to get that mass on a spring or that pendulum to start oscillating, we have to actually physically take it from this equilibrium position and bring it out to its amplitude position and then let it go at a time of t equals 0. So that's why we usually use cosine, because cosine does start at that amplitude position and then it starts going and starts oscillating back and forth. Sine, you can see, starts at the equilibrium position. So that's why we're usually not using sine in that equation for displacement as a function of time. So let's talk about some more definitions. I already mentioned a lot of these and you have heard them before, so this shouldn't be as new as some of the other ones might have been. So amplitude was, remember, x sub m or r capital A. This is the farthest distance from equilibrium. That phase angle or phase constant, like I said, this is only present because we want the equation to be true regardless of where the particle is in its oscillation when we happen to set the clock time to 0. So for example, if time is equal to 0 when the particle is at the x maximum or our amplitude position, our phase constant is 0. And like I said, this is usually the case. Now, instead, if say time equals 0 when the particle is at a negative x maximum, then our phase constant would be pi radians. And the reason for this is if we look at the cosine graph here. So we're using our displacement as a function of time equation, and it's the cosine, it's the amplitude times the cosine of the whole phase, which was omega times t plus the phase constant. If we start at a positive amplitude position, like the cosine graph is, our phase constant would be 0 because we don't have to shift that graph at all. However, if our time starts when our particle or our square or whatever we're talking about here, is at a negative amplitude position, which would be here, we have shifted a whole pi radian. So that means our phase constant has to be pi radians now because we have shifted that graph. So that's what that phase constant is. Okay. Angular frequency, omega, you have seen this term before when we talked about rotational motion. This is the magnitude of the vector quantity of angular velocity. And we know that velocity, when we were talking about circular motion, can be written as our displacement over time or distance over time. In circular motion, that is 2 pi r, the circumference, over the period. So here we now have angular velocity equals 2 pi over period, because again, we can relate angular velocity and linear velocity by our radius as well. And then of course we know that period and frequency are inversely related, so we can also write this with frequency. So our angular velocity omega is equal to 2 pi times the frequency. So velocity of simple harmonic motion, we know that if we have the position function or the displacement as a function of time, we can just take the derivative of that equation to get the velocity equation. So if we take the derivative of this, we have to use the chain rule in this case. So we take the derivative of the inside and then multiply it by the derivative of the outside. So we end up getting the velocity as a function of time in simple harmonic motion is equal to negative omega times the amplitude times the sine of the phase, which again is our angular velocity times time plus the phase constant. So this is the equation for our velocity as a function of time in simple harmonic motion. Now here we can see that velocity depends on time because the sine function varies with time, and the sine function is going to vary between a positive one and a negative one. So because sine varies between a positive one and a negative one, this tells us that that quantity in front of the sine function determines the extent of the variation in velocity. So velocity is going to vary between a positive omega times x maximum or times the amplitude and a negative omega times x maximum or the amplitude. Now, if we think of this in terms of rotational motion, and like I said, the crash course simple harmonic motion video does a really good job of this, x maximum can kind of be thought of as a radius, like the amplitude from the equilibrium position. So if we think of that as a radius, we can see that we are actually relating our linear velocity with our angular velocity here. So we know linear velocity is angular velocity times radius. So this is why we are oscillating between a positive omega times our amplitude position, which is the maximum distance from equilibrium, and a negative omega angular velocity times the amplitude position, okay? So we call this the velocity amplitude or the maximum velocity. That's going to be the angular velocity times the amplitude position of the motion, or amplitude of the motion, I mean. Velocity is at a minimum at the two extreme points, and we can see this when we look at the GIFs that I've put in this video, or just think about, something that's oscillating back and forth between two amplitude positions. We can see that at the amplitude position, we stop and turn around, stop and turn around. So at the two amplitude positions, we have a velocity of 0. So that's where our minimum velocity is. And then our maximum velocity will be in the very center, which we already talked about. And that is because that's our minimum force, right? We have no force at the center. That means our velocity is at a maximum. And then the object is going to start slowing down. And then again, comes to a 0 point. And then it starts speeding up. Maximum through the equilibrium, slowing down, and then 0 velocity at the ends. We'll talk about that a little bit more in our next lecture, which is the energy in simple harmonic motion. All right, acceleration, just how like we took the derivative of the position function to get velocity, we now take a second derivative of that function to get acceleration. So again, using the chain rule, we have to take the derivative of the inside, multiply it by the derivative of the whole thing, and we get that the acceleration as a function of time is a negative omega squared, angular velocity squared, times the amplitude times the cosine of the phase, which again is angular velocity times time plus phase constant. Now, the variation in magnitude of acceleration is set by acceleration maximum of omega squared, so angular velocity squared times the amplitude. And this is, we kind of talked about this with velocity, but this is because cosine will vary between +1 and -1. So that means the maximum is going to be equal to this right here, maximum acceleration. So acceleration is 0 when x equals 0. And we talked about that again, because we know that at that equilibrium position, we have no force. So because we have no force, we have no acceleration. And that acceleration is at a maximum when we're at the two amplitude positions, because we have our maximum force and therefore we have our maximum acceleration. If we combine this equation here with the position equation, we can then get an equation that's even more useful for acceleration. And that is this equation right here, where we get acceleration as a function of time is equal to a negative our angular velocity squared times the position as a function of time. So this is not maximum here. This is the position as a function of time. So in simple harmonic motion, acceleration is proportional to the displacement, but opposite in sign. And the two quantities are related by the square of the angular frequency. So that's what this equation tells us. Now let's talk about force a little bit more in simple harmonic motion. I talked a little bit about this before, but remember the direction of the force is proportional to the object's displacement, but opposite in sign of the direction of displacement. I kind of just spoke about this with our acceleration, right? So back here, in simple harmonic motion, acceleration is proportional to this displacement, but opposite in sign. So we know that since acceleration is pointed in the same direction as net force, it's going to be the same for force. So what this means is we have a restoring force. And I've talked about a restoring force before when we talked about spring force. But like I said, this applies to something like a pendulum as well. So we're trying to restore the object back to the equilibrium point, which we call x equals 0. So for example, if I have a block on a horizontal spring here and I pull that block back, that spring force is trying to restore that block or the spring back to the equilibrium position. So we can see that our displacement is positive, but our force is negative. If we do the same thing, but push that block to the negative displacement, the negative direction, then we have a positive force. So force again is proportional to the object's displacement, but opposite in direction, so opposite in sign. So what we can get here is the force is equal to mass times acceleration from Newton's second law. And then of course, acceleration can be written as this. So our negative omega squared times x, which we saw on the slide 2 slides ago. And so just rearranging here, we get a negative mass times omega squared times x. For a mass on a spring, if you recall Hooke's law from chapter 8, we know that force is equal to negative kx, where k is the spring constant, x is the displacement from equilibrium, and that's a negative because the force is a restoring force. And then if we set this equation right here equal to this equation right here, we can then get an equation for our spring constant k, and k will be equal to mass times angular velocity squared. So rearranging this, we can get that angular velocity is equal to the square root of k over m. And then we can also relate this to period as well, because we know that omega was equal to 2 pi divided by period. So we get that period is equal to 2 pi times the square root of m over k. So these are some other helpful equations. These ones down here, though, are particular for a mass on a spring because we are using k, which is our spring constant.